what is now available for to perform reactions, as I've said initially, is the pi electron density above and below the alkene plane where the substituents are located. So in general, this pi bond is of course made up of electron density, so it has a nucleophilic character. It looks for a positive charge, or at least a partial positive charge, to react with. So in general, pi bonds act as nucleophiles and they react with electrophiles. Of course, substituents that push electron density, so for example these methyl groups that have a plus I effect that push electron density onto the double bond, they enhance this nucleophilic character, because more electron density means more electron density that can react with something. And in opposing to this are groups that withdraw electron density, for example like these fluorine atoms. They withdraw electron density, so they lower the nucleophilic character of the pi bond, and this acts as a weaker nucleophile. And in general, these are then also less reactive, at least in the terms of the electrophilic addition reactions. So in general, we see this reactivity. We see the electrophilic addition reaction of alkenes. So in the first step, an electrophile gets attacked by the electron density in our pi bond in our alkene and is added. We are forming an intermediate alkyl cation, so a carbocation here. And in the second step, this intermediate carbocation, as we've seen it for the SN1 and E1 reaction mechanism, gets attacked by a maybe negatively charged nucleophile, so that in the end we formally add an electrophile and a nucleophile to our double bond, and our double bond is of course consumed during this process. And the same reactivity can be seen for alkenes. They of course have basically two pi bonds, so we are not generating an intermediary alkyl cation, but a vinyl cation, and this can then also get attacked, and of course again one of the pi bonds is consumed. And here at this double bond, again the same addition reaction can happen, because this is basically the same as an alkene that we've seen in the first step here. So we can conclude the electrophilic addition reaction is basically the reverse of the elimination reaction. In the elimination reaction, we are eliminating something to form a double bond, and in the addition reaction, we are adding something to the double bond while the double bond is consumed. And the easiest example to understand this, how we can exploit this, is the addition of an acid molecule. For example, here in general HX, but this can be in a real case. This can be, for example, hydrochlorine or hydrobromine, like hydrochloric acid. And if we dissolve our alkene in this acid, then our double bond, our pi electron density, can interact with this positively charged hydrogen. So in most cases, this will be a proton. And the proton acts now as our electrophile, adds to the double bond, and we are forming in this initial step our intermediary planar carbocation. This is positively charged, as the name carbocation already suggests. And in the second step, which is then fast, our X, which is negatively charged, now attacks our carbocation here, and then we formally add HX to our bond. Of course, this reaction is not stereospecific, so we are getting, if we are producing a chiral carbon atom in this maze, during this reaction, we are getting a racemic mixture of our halogene alkane. And how this looks on the orbital side, you can see here. So we are having here again our pi bond. This interacts now with the empty sigma star orbital of the HX bond, and we are forming for the intermediary phase, we are forming a new sigma orbital for the newly formed HX C or carbon hydrogen bond here. And as we've also discussed in the recap, we are having this empty p orbital at our carbocation here, and with this empty p orbital, the electron density of our X minus can now interact, and here we also form the new sigma orbital of the new carbon halogen bond in general. So this is how we rearrange from a pi orbital to two sigma bond orbitals in this case.